So I'm Amir. I'm an associate professor with the Department of Biomedical Engineering at the University of North Texas, but I've been doing robotics for the past 20 years or so. So a little bit about myself. I received my PhD in robotics from an institution called Italian Institute of Technology. And then I moved to Swiss Federal Institute of Technology in Zurich, ETH in Zurich. And I was there as a postdoc. The lab then moved to University of Cambridge in UK, but then I moved to Singapore, Agency for Science, Technology, and Research, A*STAR. I was a scientist there. And then 2016, I moved to US as an assistant professor with the Department of Mechanical Engineering at UT San Antonio. And 2021, I joined UNT as an associate professor. And this is me. And that is a robot that I started my PhD working on. This robot is called ICAP, ICUB. Let me show you a video of ICAP first, and then I'll explain what I was doing.
The problem with robots is that they just don't think like us. Okay, sure, so they can remember directions and walk around, but they can't look at a table and say, oh, that's a table, I'll put some coffee there. Well, they couldn't before. Meet iCub, a robot so clever he can tell the difference between building blocks and an octopus. It sounds simple, but that's a very human process of thought and learning, and it's not something computers are good at. iCub is. With just a little help from his creator, Professor Giorgio Metta from the Italian Institute of Technology, he can learn what things are and even play with them.
What we wanted to do is to make sure the robot can interact with the environment, has plenty of sensors like cameras, microphones, a skin that can feel touch and pressure, and use these sensors to understand whether the robot is doing good or bad and improve his behavior.
Okay, so he's still a long way off learning how to make a good cup of tea or hoovering the house, but he is a rather remarkable start.
So I'm going to stop here. At the very end, you saw a person giving a robot, handing over a ball. This is a very simple task for a human. It's a very, very complicated task for a robot to do. And I will show you later. So I'm actually using AI. My field of research was in robotics. I use AI as a tool. And I will explain later that why I don't believe that AI itself is a solution. And we need something else on top of AI. I want to start with this. What is a robot? Next, ask you, can you give me a definition of robot? What do you consider as a robot?
A machine that's programmed to do a specific task or set of tasks.
So a printer is a robot?
No, that's a consumer product. So
I was going to say a robot is a device that is programmed to do a task that would normally be done by a human being, but it does it more efficiently.
Okay, so if you want to do something efficiently, we give the task to the robot.
Generally, yes. Like what you're showing there, there used to be human beings assembling cars on the assembly line, okay, an auto manufacturer, but now most of those tasks are done by robots.
Good point.
Back when robots were first talked about, before they were a possibility a long time ago, it was usually a humanoid type robot, right? But now the definition has become more broad, right?
Yeah.
Yep.
There's some things that you wonder why they call it a robot. They call it a robot. Yeah.
Yeah, I think a robot is more than a device. A robot should be able to interpret its surroundings and then modify its behavior based on surroundings.
That's a very good point. So I'm going to show you a video. This is an assembly line. So this is an assembly line at BMW. You see the robots. And based on your definition, they are not robots. There is something here strange. I mean, I wonder if you can notice that. There's something strange about this.
There's no humans around.
There is no human. Is it because they do the job more efficiently than humans, so we don't need human?
It's too dangerous.
Very good. Why?
A lot of robots today, they don't know. They don't have the intelligence to not hurt somebody or not hit somebody or run into somebody or be soft in there.
Intelligent. So you mean
interactions and stuff.
AI could be a solution because it's artificial intelligence. So if we make them more intelligent, we could solve the problem.
I don't know, but there are some cobots today, right, that do have some of those capabilities.
Yeah, that's my point. Can you example one of give me an example of a cobot?
Just, I've already seen some demos of.
What about those little carts that move meals around at UTD? They stop if you walk in front of them and they sit there and beat for a while and then they figure out that you've gone and they keep going.
Good point. Any other?
I think some military applications, similar to what he's saying, but also for like drones that monitor space in dangerous airfields and like.
So we have cobots that they can collaborate with humans safely. Why we don't have it there? Why there's no human here?
Hard to stop them.
They're doing fairly heavy work and fairly, so yeah, like it's difficult to.
Those are like autonomous systems?
Yes.
Okay.
So they are pre-programmed. Everything
Pre-programmed.
is pre-programmed. Yeah. So these type of robots, and basically, so you mentioned human and robot, but basically, if I say the word robot, the first thing that comes to mind is this type of robot because they were the first type of robots introduced in our daily life, industrial robots, and they are very good for this type of task, like pick and place, pick up the subject from this point and put it there. And this is what we call position control. But we only care about position. Take it from here, put it over there. If this one instead of here is here, then we have a problem. That's when I say, okay, put a camera there, the object is not here, move it there, pick it up. Yeah, AI can actually help us to some extent. But the real problem, and all those cobots that you mentioned, there is something that is missing, and you never see that in any. I mean, I challenge you to go and find something like this. So you see Boston Dynamics. They have this Spot robot, and they have Atlas humanoid robot. Recently, we have this Figure 1 robot, super intelligent, super smart. The robots that they deliver food, those drones in the military, find one of them that they can physically interact with humans. You will not find one video as that example. And
What about the robots in Japan? They keep showing talk to humans.
talking to human.
Yeah, talk.
Yes, yeah, but we human, we don't only talk to each other, we also shake hands. If we want a robot to be in our daily life, we need physical interaction.
Isn't part of it motor technology?
Yes.
The technology and the motors that drive them has to more to make them safe around.
Very good. So this is a video from DLR. For those of you who don't know DLR, DLR is like NASA here in Germany. It's a German aerospace company, and they are very advanced in robotics. I was there during my PhD for 6 months. We did this type of experiment there. If we have a robot just close to human, what's going to happen?
Break the first rule of robotics. You shall not harm a human.
Wow.
Oops.
Yeah.
So definitely there is a problem. How do you think we can solve this problem? The one to be around human and be safe for human. How can we solve this?
More sensing.
Yeah, more sensing and feedback. Like what kind of sensors do you think we should use? Vision, like cameras. Yeah.
Yeah.
What else?
Vision sensor and also touch sensors.
Yeah.
If you are making contact with something soft, you have to stop or push back.
Yeah. So you could put actually force sensor. They have force sensor here. The force sensor. The problem with that is, and all other things, is that for sensor to sense something and then send it to the control loop, and then the control loop send the signal to the actuator. It's a loop. It's called control loop. It takes time.
Yep.
It takes time, about like 25 milliseconds to 250 milliseconds. Yes.
What about like in humans, how we have reflexes and it just goes to our spinal cord, short going to our brains? Do something like that?
Yeah. So you're actually, I mean, probably you're talking about the CNS, central nervous system. We are doing so many things, not by our brain, but our spine. I will explain it later. But no, this is something not about this. It's about this control loop that takes time. And I would say 99% of all the actuators being used in robotic platforms are electromagnetic actuators. And electromagnetic actuators, they tend to spin really fast, but they don't give you enough torque. So what we do is spin very fast, but they are very weak, not as opposed to powerful, weak in terms of the force that they can provide. What do you think is the solution for that? How do you think they solve that problem? Because if you use electromagnetic actuators, it's going to be really fast, but very, very weak. But you saw that those robots, they can pick up heavy object. What they use to solve that problem? You see them everywhere. Even in your car, you have them. Gears. So gears, the job of the gearbox is actually to slow down the spin, but give it more torque. Okay, so it's just torque and velocity. You decrease the velocity, you increase the torque. But then there's a problem with that. Is that what we call reflected inertia? Reflected inertia. Inertia is resistance to motion. So if I have this chair and I want to move this chair, I have to apply a certain amount of force to move it. But this one, I can easily do that. So this has less inertia than this one, or mass, but inertia is a broader term. Or if it is moving, if I want to stop it, this is harder for me to stop with this one than this one. Reflected inertia is some kind of inertia that is hidden. You don't see that, but it's there. I can give an example. What's this? The name of this toy that? Yes. It's spin. So let's say that you have this, like the diameter is 5 centimeters, and then you can easily spin it. And then once it's spinning, you can actually put your finger there and stop it. Okay. Let's say you connect that one to a gearbox with a ratio of 10. And ratio of 10 is really, really small ratio. Those robots, they have ratio of like 2,000. Ratio of 10 makes that small toy with a diameter of 5 centimeters, 5 meters. You're going to feel that if it was a disc with 5 meter diameter, that is a reflected inertia. That's the hidden inertia. So if you connect that one to a gearbox, that's how you're going to feel that. So we think about like 2,000 ratio. So that's why if we put a sensor there, vision, camera, tactile sensor, whatever, it's not going to help us because it takes time. It's like a huge truck coming towards you, and before the driver can actually stop the truck, the accident happened because they are moving fast. And when you want to stop it, it takes time. The inertia is really hard. So so you mentioned the actuator. Yeah, the source of the problem That's the question that I wanted to ask actually throughout this presentation. It was actually the actuation part of the robot. And I'm gonna show you another type of robot, humanoid robot. So some of you may have seen this one. And back to, I think, 90, the Japanese actually introduced that. They were so proud of this. And you know the price? 2.5 million.
Whoa.
Piece of yes. This is a video of us.
Yeah.
Technology, making better, better. Onwards, upwards, any way but backwards. Tapping progress on the shoulder and saying, more forwards, please.
That was a very impressive video by Honda, but the problem with this is that it's fake. This is not real. The real Asimo is this one.
私、アシモのことをたくさん知ってもらいたいと思います。私たち人間にとって自然に思える動作、歩くということ。2本の足を交互に出して歩く。段差や階段を登る、降りる。凸凹な道や坂道を歩く。歩くといっても、実は人間はさまざまなバランスを足で取って歩いているのです。だからロボットにとってはとても難しいことなのです。その2本の足で歩くということを世界で初めて実現したロボット、それがアシムなのです。今私は足の裏のセンサーで階段を確認し、うまくバランスを取ります。皆さんついていないでしょうけど、人間も目を見て速さに合わせて足の裏でバランスを取りながら。それではご見学中のお客様に申し上げます。ただいまロボットが点灯したのでステージを
And that was the program. So he knew everything, but yet they couldn't actually make it. And the problem was one of the stairs, like the height was not precisely, and then it was not able to accommodate for that small change. But we human, we can easily do that. And again, the reason is not because of the AI technology, or like this is not smart, or we don't have enough sensors. And the real problem is somewhere else. And it's not only Asimo. This is DARPA Robotic Challenge, and they are like humanoid robots from leading robotic institutions, MIT, Japan, coexist in Korea. And this is a funny video.
It's relatively current, but this is state of the art. It's 20.
Yes, I do.
Here's
I have a question. Sure. I've seen LinkedIn posts by Boston Dynamics that show the progression of their robots. And the latest one showed the robot pretty functional. Are those fake or
No,
am I missing
those
something?
not fake. Those not fake, but you don't see they're interacting with humans. Everything is pre-planned. If you change something, and by change I mean a dynamic change, it's something that is constantly changing. They cannot do that. So I'll explain later why. I mean, what's the reason behind that? So let me ask you this question: if you have the most advanced AI, and you could put it on. You have two options: you put it on the body of a human, and make it a super smart human, or a body of a dog, and you make it a super smart dog. Same AI. Which one would you choose to have a smarter creature? A body of a human with the most advanced AI on top of that, or a body of a dog, the most advanced AI?
Depends on the task.
I was going to say, depends what you need. Or what task?
Yeah, right. What's the test?
In general, which one do you think is going to be more capable of doing different types of
More
things?
mobility or more like mobility is difficult as a human. Dog's way easier as a robot.
Let's say that only one of them could survive. So they have to fight and only one of them could survive. They have the same level of intelligence.
Got to be a dog.
Why?
Because of stability. You've got a more stable base.
Yep.
The chances of surviving with 4 points of contact are going to be greater than just 2.
But there's many things that human can do that dogs cannot do. Dog cannot play piano. We are maybe the only bipedal creature, like we are using 2 legs, like kangaroos, like jumping like this, bipedal. And this is really a difficult task. It's not only the brain, it's also the body. We call it the intelligence that we have in our embodiment. We human, we are the smartest animal on the planet, not only because of the brain, it's also because of our body. Our body is smart, it's really smart. And you mentioned the CNS. Something like walking is a very difficult task for a robot, but somehow when you grow up, it's going to be programmed into your spinal cord. And when you're walking, then you don't really use your brain. Walking is a very challenging task, very computationally extensive task, but it's being done by your body, not by your brain, because our body is really smart. Another example for like AI. Do you know this guy?
Gary Kasper.
Yeah. So it was like, I don't know, leading chess playing the board when I was young. And you know this guy.
Lionel Messi.
And so which one is the smarter?
Well,
How do you
I think Casper. Yeah.
Good point, nothing. Usually we think about like who is using the brain is more smarter. We had Deep Blue. Are you familiar with Deep
Yes.
Blue?
Yeah.
I was going to say he lost to Deep Blue.
Yes.
Lionel Messi.
Yeah, and do you know what year was that? That he lost to 97.
97.
Yeah. So we had Deep Blue outperforming this guy. I'm gonna skip this video. It's about Gary Kasparov losing to this Deep Blue. And now, 25 years later, this is Robocop. And also can actually, instead of me showing this one, I could actually show Boston Dynamics, but still compare that one with this one.
Looking to start the break in.
the level of performance of this versus this, or even plus and minus.
You need a new goalie.
I know. Turn him on. Wow. Yeah. You have to see the goal against Getafe. That's one of his best goals.
And by dynamic environment, I mean something like this. Everything is constantly changing.
And the split second decision making.
Yeah.
is unbelievable. Right in the corner. Holy cow. Haven't
So-
seen half of it. Yeah.
So what you're suggesting is we don't have to worry about these Boston dynamics.
What you need to worry about, what I'm saying is that they are not as promising as you think. I mean, there's still some part, some component that is missing. And without that, we still cannot have robots outperforming humans. It's not only about the brain, it's also about the body. It's about the mechanical structure of the body.
So where you've got a fixed constrained environment, robots building Teslas, for instance, that's great. Where you don't have humans involved, but where you've got a dynamic, changeable environment.
Yeah.
It's a different situation. And
It's a whole different situation. If you have robot in,
What if you looked at something like sixth generation fighter jets? Don't even have a pilot and are connected to a network. At some levels, they're autonomous, but they also coordinate in a battlefield that's very dynamic. Do you consider that not a robot?
so yeah, that's a robot. That's a good point. That's a very good point. But I don't know how what's like the time frame that they have to respond. Like what's the
Pretty immediate.
Yeah,
The missiles coming out.
Yeah.
Have you guys ever, I was intrigued when you were comparing, vertebrate animals, dogs. I've heard, I'm not an expert on octopus intelligence, but have you ever heard that
I have it on my slide later, yeah.
Oh, okay.
Yeah.
They have a distributed intelligence.
Mhm.
that-
Really?
Yes.
Yeah. So how's it distributed?
each limb is independently operated on its own.
Really?
It sounds like, I was gonna ask him if he was gonna talk about it.
Yeah,
Sounds like
no,
you are.
I have it there, so, yes.
I was hoping that you were going to speak on something like this, and more to the fact of having seen A2 RL.
Yes. The robot?
No.
They
These,
have a robot called A2.
these are racing cars, autonomous.
Okay,
If you're doing that, this is nuts. If you're driving a Formula One
okay.
autonomous.
Yeah.
That's not fair.
But let me ask you a question, and so to your point. Is any human involved in that scenario?
In the training.
Once it's trained, the car is released.
But is there any human involved? That's my point. You
After it
see
leaves-
human here.
After it leaves the pit. No.
But are they?
No.
Why not?
My personal opinion, based on immediacy, distributed networks, where the intelligence really is and how fast decisions can be made, putting a human in the loop actually makes it more dangerous.
Yeah, but I mean, there's one point missing here. It's like in some scenario, your job is to kill human. Another scenario, you want to be safe.
I think that there is always some sort of a command control station where human beings are at least at point of launch.
Yeah, but he mentioned that if you put a human in the loop, that was your point? That is not
For the mission.
for the mission. Yeah, so
Now, if you need to, if you get a phone call from the president that says disengage, somebody's gonna enter the command and control center and change the script. Yeah.
Well, believe it or not, there's one human in another race. So it's the autonomous car, race car versus,
If a human suddenly bump into that car, what's going to happen?
they've already had accidents.
So they already have accident. Okay, so here the point is not having,
All running
it's not,
the other driver.
so it's,
We're talking closed circuit racing. People are not supposed to be.
No, we're talking about full racing, Formula One.
Right, but it's
Yeah.
a closed circuit, meaning there's not supposed to be pedestrians or
Yeah.
other environmental variables that are out of control, right? It's a,
Pedestrians on the track.
yeah, that's what I'm saying. It's a closed.
There are pedestrians in the stadium, yeah.
But there is debris and there's cars that have spun
But
out.
again, it's limiting environmental
I think
interaction.
the point is, where is the intelligence? And how far down into the processing is it? So that decisions can be made faster. And then that information may or may not be set back up.
but my point is that the intelligence is not the thing that we are missing here. It's something else. So the thing that I want to talk about is like in those scenario maybe, but in robotics is not. In robotics is the body of the robot. That part is missing. I don't know if they could use the technology that they have for Formula One or for the fighters, if you could use it for robotics. I've never seen that. I've never
Well,
seen.
it's not Formula One per se, they don't have anything to do with it, they're using Formula One car.
But the technology that they are using for Formula One cars, if they could use the same technology for human robot interaction,
Like I said, it's coming.
that's a different scenario. That's my point. That's the difference in the body, right? Yeah, that's all I'm saying. You need the body.
There's a local. They're quite interesting. I have an autistic child. Robokind, I don't know if you've ever dealt with them. But what they do a really good job of is that human interaction.
That's not physical interaction. That's cognitive interaction. That's not physical interaction. We're talking about physical interaction. I know about those robots. Yeah.
But the facial expressions and all that.
Yeah,
type of
yeah.
stuff.
Because I think those kids they get overwhelmed with all the information they get from the human face. So
Right, so
the
they wanna
robot.
keep it-
Yeah, they can get it simple, but that's cognitive interaction, not physical interaction.
Going back to the
Yeah.
military application, we're talking about where is the intelligence? It's not localized from what I understand, it's distributed among the different devices and assets that are floating around, for example. Some of that could be in the missile, some of that could be in airplanes. Yeah, some of that could be in ground stations, some of that could be in satellite, but all of this is networked to ultimately derive at what you want to do with your target.
So maybe we have different understanding of intelligence. When you're talking about the distributed fashion, like you have like the octopus that you mentioned that actually have some level of intelligence even in the body. My view of intelligence is something that you think about like the computations. You get some inputs, you get some outputs, and inputs is some data, and then output is also some data and information like common. But there's also another type of intelligence is for the body. You give the body some kind of input, and the body is going to react to that. And that reaction is physical. Means you have motion and you have force. You need to have these two components for physical interaction. That type of intelligence is missing in today's robotic technology. That you give it some information to the body, and the body then reacts to something. I don't know if you have heard of this word, passive walker. Have you heard of passive walker?
Passive.
Walker or is a bipedal robot that can walk, and it's passive. There is no actuator in that. It can walk by itself, but on a ramp. So the gravity is the activation force here. But you have to design the body in such a way that it can walk, and it walks really, really similar to human. So this is what we call the knee bend. It's very unstable type of walking, but that works really like human because we actually use passive dynamic or passive walking for locomotion. And that's only about the body. There's no brain in that. There is no actuator in that. It's all about body. There's one type of robotic research that they only focus on the embodiment. How do you design a body of a robot that with simple input, you can get complicated output. And that's kind of intelligence I'm talking about. And one of the things that is necessary there, and without that we cannot do anything, is the softness in the body. And you mentioned octopus. Octopus is able to do that because it's soft. The softness in the body is really, really important. Not only because of the safety, so all those robots that you see, they are dangerous. One of the reasons is that they are very bulky, they are very heavy, they are very rigid. But we human, we are soft. Our actuators, the muscles, they are soft. So softness is really, really important. And my research is on soft robotics, and we can have soft robotics for different types of application. What I'm going to do is all about physical human-robot interaction. You can think about exoskeletons, rehabilitation robotics, surgical robotics, collaborative robotics. But again, with cobot, I mean not only cognitive, but also physical interaction. So again, the problem that we have is the gearbox. This is one of the gearbox. It's called harmonic drive. It's actually a company in Germany. They have this system, and because they have patent, they are the only one.
Wait.
It has 3 components, and they can get it any ratio actually in a very compact space. I think nowadays every robot they have this harmonic drive, and that's the problem, because that is going to give us really, really high reflected inertia. That's the source of the problem. And here are some examples of physical human-robot interaction. This is what I mean by physical interaction. And as you can see that this is in a lab setting environment, and it's very, very slow actually. But again, doing something like this is challenging. It's like a big body of robotic research being dedicated to this physical human-robot interaction. All these robots, they have this gearbox, and that's why that makes it very, very challenging for us to make something like this. We think that this is very easy for a robot to just push the robot and then it moves away. But no, it's a very, very complicated task to make it happen. This is kind of technology that I developed in my lab. It's called actuator with adjustable stiffness, or always with this type of actuator, we can actually, it's kind of soft actuator, but it's soft because we have spring inside that. It's like compliant, but we also can change the level of softness. Sometimes it can be very, very soft. Sometimes it can be very, very rigid. So we actually have another actuator within this big actuator to change the softness of the actuator. And if we can make it very compact, which we did it, you can use it in like bipedal case. Different type of language. So with this one, for the control, we use C, C++, and that's because of like we need to be very fast. But you can even do it with MATLAB. There's no specific language or Python. This is not. These are not really a kind of task that challenges about program. What we did is actually simply a sinusoidal trajectory for that. Yes. And the other thing I'm doing is actually using the same technology for rehabilitation application. This kind of unique treadmill that I have in my lab. And with this treadmill, it's actually a dual belt treadmill. So if we have 2 belts, we can change the speed of each belt independently. And we have motion capture system to actually analyze the gait of the person, how this person is walking, but when it is unique. And also we have this lightweight system here to cancel the weight of the person from 0% to 100%. So the person does not need to carry his own weight. But what is unique is actually we can change the surface stiffness. So basically it's going to mimic for you the way you walk on sand or mud or grass or foam, because this is beneficial for people like they have mobility impairment because of the stroke. It's the same type of technology that I had for the actuator. We did it for this thread. And going to the octopus, so these are all about actuators where we're just adding some kind of spring inside that to make them behave soft, but there's another part of robotic research on soft robotics to make it intrinsically soft. And actually that has started with octopus. What is unique about octopus is what we call degree of freedom. So degree of freedom is basically how many active joints you have. So for instance, look at my arm, I have 1, 2, 3 maybe, and I have 3 degrees of freedom. Octopus arm has infinite degree of freedom. And that's because it's soft. So it can do many things because it has infinite degree of freedom. There are different types of soft actuators. And we use intrinsically soft material, but different stimuli. Like it could be electromagnetic, it could be pneumatic, it could be temperature here, and also this one. This is a new type of research to make the robot soft because we think the real answer to that problem that we have with the actuation is the muscle. And the idea is if we can make a humanoid robot with soft and artificial muscle, that could really enhance the functionality of a robot. Yes.
But that's to do with the biology of the actuation mechanism, isn't it? It's not the material the muscle's made of, it's how you actuate the muscle.
Yes,
That's
yes,
important.
yes. And that was a very good point because all of these that you see, like it could be electromagnetic, heat, light, whatever trigger that you can think about, the current technology, we are still not there, I would say, because of it takes time to heat it up. The electromagnetic soft actuators, they are not enough strong. This one that you see here is really, really strong, really, really fast. It needs 400 kilovolts to be activated. So these are the problems that we have. So there's still no actuator that you can compare it with human muscle that can give you same amount of force, same amount of deflection, the same amount of speed with the same amount of energy as the input energy. There's still a ton of research in this direction. And again, the idea is we need it to be able to make robots more interactive with humans. And that's actually one of the things that I developed in my lab. It's called electromagnetic soft actuators. What we have is actually we have a pipe made of silicone. It's like a rubber. It's 10 meters long and the diameter is 0.1 millimeter. It's very, very tiny and 10 meters long. We have E-gain. E-gain is eutectic gallium indium material. It is a conductive material and it's liquid. We put it inside this pipe and we have a wire, flexible wire. And then we wrap it around and then we have a flexible magnet that we made in my lab. And then when you put this flexible magnet inside that coils of the flexible wire, this one, and you see this like the type of functionality that you get from human muscle. You have like 2 magnets, electromagnet. They attract each other, reverse the direction, they repel each other. This kind of linear motion, and then you can bend it, you can hammer it. The problem with that is that the force is not enough. The force compared to the human muscle is not enough. But we found very interestingly that if we reduce the size of this actuator, if you make them smaller, yeah, because
you might be getting to this, but the reason one of the reasons there's different strength levels in people is because you can actually put more of these parallel. That's why stronger people have bigger muscles. So I think you're going to say if you make them small enough, you put 4 of them together.
Exactly.
Stronger muscles.
Yes, yes. So we found that if we make them smaller, actually the force divided by the size, that ratio is going to go up. So it means that if we make them small and make a network of actuators, that is going to give you higher force than a single big actuator. So if you make them,
I hate to ask
yeah, sure.
dumb question,
No, it's not.
but in taking a look at someone was during the last part, always told me to think smaller. Have you ever thought about how nano type cells or
Submolecular.
are able to actually manipulate themselves and grapple the other cells?
Yes, this is
Manipulate
Other things that are 100 times their size. Their size as a nano particle. Have you ever thought about taking that same technology and bringing it, expanding it? To the human side. Because they're doing the same thing that you want to do.
Yeah. Yes. We always look at nature. We always look at like different motions in the nature.
But that's not nature because that's a nano thing that's not.
But in the human self.
Yeah.
Yeah.
Somebody has created a nanobot that actually can go in, grab a hold of the cell, and do something with it.
Oh, so you're talking about the nanobot. Okay, so that is another story. With all of those nanobots and microbots, they put it inside the human body. Yeah. Where is the battery? How do they move that?
So I was going to ask one step beyond that. So
Yeah.
now with quantum mechanical engineering, where you're going subatomic, right?
Yeah.
Any thoughts to that? Because that is essentially mitochondrial engines or subatomic engines, right? Any look at going super small to kind of carry on to
But
his thoughts?
this is very interesting. Like I'm getting some comments here that I never thought of. I just like, I mean, I'm very happy that I'm here because
Welcome to our group.
yeah. Like that gentleman
why we
over
come
there
together.
asked me about like the fighter jet. That was really good point. Never heard of that. I need to find like the reason why they didn't have that technology in robotics.
Well, I'm really curious if
Yeah.
you wouldn't take it. What is currently there?
Oh, no,
And
yeah.
like the Fantastic Four, bring it to
Yeah.
fruition.
So there's something that in the robotic community, and especially those people that they don't nanobots, maybe I should not say that. They don't tell you the whole story. I will put it in this. They don't give you the whole story. They say, guys, it's very, very powerful. Where the energy comes from? Okay, so maybe, I mean, most of the time, these nanobots, they have a strong magnetic field outside. That's the robot. The thing that you see is the moving, we call it end effector. That big picture is the robot. They don't show that. We also have it with in my field. They have pneumatic actuator. They say, okay, they have a pump, and then they put the air pressure inside. It's very powerful. It's very flexible. So basically, you have a balloon. You put the air inside. It's going to be inflated, and then you take the pressure out. It's going to be deflated. You can do it very fast. It's very soft. They don't show the pump. That's the robot. They just don't show it. It's just like they want to see it be impressive, and they put it somewhere. But yeah, think about it. The nanobot, where the energy comes from. It's from the external environment. It's from the external magnetic. They could have light. They could have magnetic field, sometimes temperature, sometimes the pH. But that is the robot. That is the end effector. That's what you see that is moving. It doesn't have the energy by itself. So that's about that one. But yeah, please.
Just on the software, artificial muscles.
Yes.
So when you're tracking the muscle, are you driving current through the coils to magnetize them?
Yes, so we have this one here and this one here. So I think here we have 400 loops here, so you can see this, and this the white one is the e-gain material. So we cut it, and so some of them still up. And the two magnets, they're gonna get magnetized and they attract each other, and then
So you're constantly consuming power.
very good point. So
And are they susceptible to increased resistance because they're going to heat up?
okay, so good point. So one of the things that they found out that when the temperature goes up, actually the resistance goes down, but to a certain point. So the resistance goes down like this, and then after that, very sharply goes up. It's better than normal copper wire. They can handle much more current than normal copper wire. But the problem is that to some extent, I can make them small. That's the smallest version we could actually make. For me to make it very small, I need a 3D printer. It's called NanoScribe, and I think in the state of Texas, only University of Houston has it. It's $500,000 3D printer that can make it in a very, very small scale. This is what we did, and I would say it's after around 100 trials. It's really hard to have e-gain in that part, and you try to wrap it around. So this is the technology that we.
Wouldn't the control system be equally as difficult to make sure that you're getting the level of accuracy
On
that
that
currents?
part,
Yeah,
on
yeah, I
that
would
part,
think-
not only this, if you have a network, let's say if you have a 40 small actuators, each one of them can be only activated for less than a minute.
Yeah, your I'm assuming you're using some type of microcontroller or something
Yes.
to try and do that, and
Yeah.
you're gonna hit the limit of the
Exactly.
speed and delay
Yeah,
there.
yeah. So as I said, all of these actuators, they are not still there. There are some challenges that to be solved, mine included. And the last one I wanted to talk about is for putting a stent. It's for surgical robotics. So if you want to put a stent, so what the doctor do is actually they can poke here into the vessel. They put what they call it the guide wire. It's a very flexible wire, and then this X-ray machine has to be on all the time for the surgeon to be able to insert this wire all the way to the heart. On top of that, they put the sheet, which is very soft. They take out the wire, they put another wire, which is a little bit stiffer. They do it a couple of times to actually can provide a very safe channel that inside that channel they can put the stent. The stent deployment system goes inside. We are actually working on a technology that is actually based on aversion motion. It's kind of a pipe that is growing inside out. So we have the air pressure here, and the air pressure applies. It's something that grows inside out, and it's very flexible. And we also have steering capability for that. It can steer left and right. But what is unique about this is that when you get to the point, to the destination point, you can make it very rigid instantly. And so you have a part that is very flexible going up, and once it's there, you make it rigid, and now you have a very safe channel to do whatever you want inside the vessel. Yeah, that was my presentation. Yes.
So what you're suggesting is Lionel Messi's career is safe for now.
Not only that, like I have a couple of, doctors, my friends. Like I have one of them is a radiologist, and he was telling me he's scared of AI. Is AI is going to take his job? I say definitely, definitely. He just going and look at the X-ray images and diagnosis. Definitely. My other friend is surgeon, and my other friend is dentist. They are doing some physical activity. No, we can't. We still need to have human in the loop. Like if you are familiar with Da Vinci robot, we have the surgeon. Da Vinci robot is that's the human in the loop.
I was just going to suggest there must be a lot of cross-pollination between the control systems they use for these advanced fighting technologies and robotics. There's a lot of synergy in the tasks you're trying to accomplish there. You can have distributed nodes of intelligence. You've got.
I would think with the muscle slide that you're showing, the other aspect is you can embed in that the actual network itself. So you don't have to have separate control networks. Depending on the materials.
This is really nice, man. I always get this type of comments when I'm presenting for the people not in my field, because they always give me some idea that I never.
Are we all gonna be on the patent?
Yeah.
It's getting straight to the point. I know.
But thank you. I mean, that was actually. Yeah, exactly. I mean, you say something, and then somebody challenges you and say, "Hey, there's another film that they're doing it much better." And oh my God, I didn't like that.
Can you talk generally about the field and your research, which is pretty specific based on the funding you get, your particular focus, and then you've got groups like Boston Dynamics, is it?
Yeah.
Where they're an ex-military or military funded initially, so they've got a different focus. And so, is there much cross-pollination?
No, I think eventually we have the same goal of getting to the point that we can have robots live with us, interact with us, physical interaction.
The example is DARPA funding company there. The internet, and everybody loves to give Al Gore crap because he said he invented the internet, right? What he was the venture capital behind the internet because he funded DARPA. It did the early work on that. So the cross-pollination that happened between the public and private, in that particular example, it wouldn't have happened without the defense industry research. But, you know, there's always, you know, the fighter jet may end up explaining how they do the control plane or, you know, nanotechnology-based muscle.
That's good. So one comment on Boston Dynamics that they're doing different approach. They're not doing soft robotics. They don't use soft materials. What they do is what we call impedance control. Impedance control is about using the actuators that are powerful, but they need very low ratio gearboxes. That makes the reflected inertia very small for them. And they have one control scheme is called impedance control. Is about, if I want to put it in a simple word, it's just taking an elastic element inside your body, inside the structure. It's just like you are. So if you're, I mean, I have a spot dog in my lab, and if you kick it, if you push it, you feel that this kind of compliant behavior that this robot has is because of the impedance control. It behaves like if there was a spring or soft material inside. But the problem with that, if something's happened really fast, then again, that control loop is not fast enough to react. So you will feel it really, really rigid. So if I hammer it, it's going to be rigid. But if I push it like this, you will see that the dog does that. And the dog is very capable of, if you kick it, it can keep the balance. It's all because of that fake softness that it has inside of it.
So what are your thoughts about the robotaxis, right? The autonomous vehicles where the vision is that to be completely on the public road without any humans? Is that a pipe dream or is it possible?
I think eventually we get there that all this machine is going to be autonomously driven. But one thing that, again, I have to think about it is why we don't use that same technology for like humanoid robot. Still, I have to figure out what's the reasons. That's really, I don't know. Until like I have to go and search what the technology they have, what technology they have for autonomous vehicles.
Mainly because of the soft body, right? Because for the car, you don't need a soft body. No, you need AI, which can you know, sense the traffic, respond to traffic, steer, right? All that stuff. You don't need a soft body. So that's the key difference.
Well, it's a lot more than that with completely autonomous vehicles. If every other vehicle on the road was autonomous, you're fine. That technology exists. It's the interaction of the autonomous vehicle with human-driven vehicles that the project right.
So it's basically like those robots that you see in the assembly line. It's like the same one if you see in the road. If you have the human, because we are very unpredictable. We can be anywhere, anytime. We can do any stupid thing as well.
But going back to the point, I think it's more easier to get there for the cars than the human being, because you don't know how to make soft bodies correctly.
Well, drive in an Indian city and then we'll talk.
Actually, I think it's easier for those people to drive in an Indian city because there's so much information that it has. Right? Once it becomes full service.
But there's also a lot more unpredictability. People follow rules here. People don't follow rules. And I'm from India, so.
But have you seen that far less accidents happen there in India?
When they do happen, people actually die. Yeah, we can talk offline.
Did you have a question?
I want to get thoughts on. Well, when I think of, or when I hear soft robotics, I think of prosthetics and how they could benefit people if they were more human-like. So I just wanted to hear what you thought about that.
Yeah, so there are two ways to think about soft robotic. One is that if the entire body of the robot is soft, or if we only use soft robotics for the actuation part, for the muscle part of that. So the exoskeletons, you could have exoskeleton with traditionally like electromagnetic actuators with the gearbox and all the control system. And you may say that, okay, it's in close proximity to the human body is not safe. So we want to change it to like artificial muscles. Again, one point, we don't have any artificial muscle right now that they can do the job just like the same as the human muscle. But if they had, that's one point of that. The other one is that to make the entire body of the robot from the soft material The problem with that is that the soft material, they cannot bear forces or weight. There has to be some rigid elements there to carry the weight or something. So like in our musculoskeletal system, we have the bones and we have the muscles. So I would say in the future, if we think about soft robotics, it's going to be soft actuators or to some extent soft sensors, but the body still needs to be rigid, like the
So
human.
there's a gentleman that used to play me, Richard said that. His name's Jim Von Air. Jim had founded several startup companies, especially in the nano space. He had a passion for the military, and he's funded privately millions of dollars for research into how to do that type of thing. And he's also endowed multiple professors in the nanospace.
Very good.
Paul can make the introduction for you. I highly recommend that.
Yeah.
Paul Button, he's famous, incredible. For what, 30 years now he's been doing this, or longer.
He's also doing a lot of work with the defense industry in the countries of ours.
Interesting.
Autonomous air and ocean going.
Good, very good. Thank you.
Yeah, you need to talk to Paul afterwards.
Yes,
He's got-
yeah, because I have a grant from the Army coming up 2025 for exoskeletons, and I think that would be really, really helpful. If I can be introduced to that.
And you were at the IQ.
Yeah.
2 months ago, yeah.
Dr. Larry at the IQ. So to talk to about the work he's doing in remote sensing.
I know. I mean, I've seen this like the biggest screen over there.
We work with Dr. Larry, so yeah.
Yeah.
Yes.
I'm a database protection.
Okay.
What kind of database are you using? And how much data are you storing per execution?
It's a very general question. Not sure, but what exactly? I mean, what kind of data? I mean, so we have kind of data that's like for the humans. Like if we have that treadmill, we have some humans coming and at least test on the human. Those type of data, like they have to be like IRB approval getting from the university, and we have to save it some safe place that the user cannot be identified. Then for like our job, we are doing basically all the data that we have is the data that we get from the sensors. It could be the data from the position sensor, from the force sensor, from the temperature sensor that we have. And
It's not a large volume.
no.
Why not? I wouldn't. Because what is making, as far as I can understand, what is making FSD from Tesla so successful? That they have a massive amount of data that the car is using.
Yeah.
As it goes through its functionality. That same thing can be applied here for every execution step that you do. You record everything. By the time that you come back to your next task, you should have lots of data.
I think that's a very valid point. But if I talk about like the Tesla, they have the platform that is already ready and functional, and then they can actually get data.
That's because they're saving your data on every car.
3 million cars every night.
Yes.
They upload exactly.
It's the difference between a commercial application and academic.
Yeah.
Well, good point.
I mean, data.
He's more worried about monetizing that data.
Yeah.
That may be true, but I'm sure Microsoft would love to give you data. I can guarantee you that.
But so I'm thinking the key difference is, I don't think he's actually working on AI. He's working on the soft, right? The soft tissue, how to create a human-like movement.
The mechanical side of it, that generates data.
It generates data, but not the style of FSD and stuff.
No, I'm not saying
It does generate
FSD, but what I am saying, an execution produces data. That execution data should be reported and
And this is one of the points that
if you don't have it, I'll be glad to talk to you.
yeah, because
I see you staying late tonight. Good points.
Yeah, because if I was like giving this speech to people in robotics, same questions over and over, but now I have questions that I never thought of. Like,
Are there any good books you can recommend on this topic?
yes, not the book. There's a guy we consider him as a pioneer in this type of research. His name is Rolf Pfeiffer. I think.
This is the default Dewey system, is it? We're going to go to Amazon and look a book up.
Let's just hear 5 minutes up.
I think, therefore I am. We all know this quote by René Descartes from school. So what he is proposing, in essence, is the existence of two separate worlds. One, an immaterial world, the mental world, the world of thinking, and on the other hand, a world, the real world, the world of physical objects and bodies. Now, throughout the history of mankind, people have always used the technologies of their time as metaphors to explain themselves, like the heart was viewed as a pump. At the beginning of the last century, many people thought that the brain functions like a telephone switchboard, and nowadays many people seem to think that the brain is really like the internet. And one way or other, we all believe that we function like computers. Now, of course, you would say, no, humans are very different from computers, and indeed, there are many fundamental differences between computers and humans, but there is one level at which it makes sense to think about computers. You have some kind of input, vision, touch, you hear something, then the brain processes the input and comes up with a certain action like uttering a sentence. So we have input, processing, output, just as in a computer. Now this is called the computer metaphor of intelligence or of thinking, and it has been extremely successful in many applications. Just take search engines, Google, data mining, machine learning, and of course, big data is the word of the day. Now, coming to more, let's say, natural kinds of skills, this approach has not been so successful. And more natural kinds of skills that we are very good at, that are very easy for us, like walking, talking, drinking, doing the dishes and things like that. Now, the research over the past 2 decades has clearly shown that rather than there being a separation of two worlds as suggested by Descartes, the world of the body, of action and of thinking are in fact intimately tied together, intimately interacting. And to characterize this relation, we use the term embodiment. And what I would like to do now is to elucidate this term embodiment. Now, I would like to give you an example. So one from Lego Mindstorms. So who knows Lego Mindstorms? Almost everybody, right? So you got these pieces that you can stick together, and you have a programmable brick. You can attach sensors, you can attach motors, and then you can actually do very nice things with it. Now, whenever you observe the behavior of a system, be it a natural system like a human being, or an artificial system like a robot, there is the question of how the behavior comes about. So what is the control that is underlying the behavior of the system? Now, I have these few examples, so let's look at a few. I have some more here. The first one we call Crazy Bird. I like him very much. Okay, so you saw very different behaviors. Now it turns out that the control is what you see in the lower right corner. It's just the wheels turning at a constant speed. Now the control is exactly the same for all 3 creatures, if I may call them creatures. but they behave in very different ways. So how is that possible? It cannot be because the control is different, because that's the same. It has to be something else. Well, it's the morphology, it's the shape, and the materials from which they're built. Now, Crazy Bird...
Yeah. So basically, he's the guy that always referred to him as a pioneer in this field. And this is a robot that he actually, I think, I forgot the company in Switzerland that they made this robot only for him. And this is activated by artificial muscles, pneumatic artificial muscles. I was like one of the first kind of humanoid robots, like artificial muscles. Yes, sir.
There's a third part to that.
What is that?
What did it say? What's the terminology?
Embodiment.
As I think. So
I am.
Will now add AI world. We are in a physical world. Now we are in a virtual. That world is something that has been produced by this. Now I can go ahead and create what I can't create.
Yeah.
Physical.
That's a good point.
I think also it's interesting as an extension into this idea of not just that our body shapes the way we think, but also our tools.
Yes.
If I have a knife, I'm going to think, how can I cut something? Or if I have a hammer, everything looks like a nail.
Yes.
All right, any last questions? All right, let's give a great